Welcome to Secrets of Earth. I'm Patrick Viersba, your guide into the world's most remote corners. Today, we travel to the oldest desert on the planet to meet a creature the size of a fingernail that has solved, on its own body, a problem that human engineers have been chasing for decades. We are going to the Namib. Here, on the southwestern coast of Africa, the landscape is a sea of towering apricot-colored dunes, some reaching nearly 1,300 feet into the sky. The Namib has been an arid environment for approximately 55 million years, making it, by scientific consensus, the oldest desert on Earth. The Sahara, by comparison, is young, a few million years old at the most. While other deserts formed and reformed with the shifting of climates, the Namib has been dry since before the ice ages, before the emergence of most modern mammal lineages, before almost everything we recognize as the modern world. It is a place of extremes. The central Namib receives less than 20 millimeters of rain per year, in some zones less than half an inch. To look at the landscape is to see a world that should be incompatible with life, and yet it is one of the most biologically interesting places on the planet, precisely because it is not fed by rain. It is fed by fog. Roughly 180 days a year, the cold Benguela Current, a massive upwelling of cold water running northward along the African coast, meets the scorching air of the desert interior. The temperature differential causes moisture to condense into a thick white fog that rolls off the Atlantic and penetrates as far as 100 kilometers inland, ghosting silently across the dunes before the sun burns it away. For most of the Namib's residents, this fog is life. It is the only reliable source of water in an environment where rain cannot be counted on. And for a family of small beetles that have been living here since long before the first humans set foot on this continent, it is something more. It is an engineering problem solved. In 1976, a biologist named Mary Seeley made an unusual observation while watching darkling beetles on the Namib dunes at dawn. As the fog rolled in, a particular beetle, Namib unguicularis, a smooth-shelled black darkling beetle, climbed to the crest of a dune, turned to face into the wind, and tilted itself forward at a roughly 23-degree angle. It raised its rear end into the air and lowered its head toward the sand. And then it waited. The behavior is called fog-basking, or the headstand posture. And in the decades since Seeley first documented it, no other beetle species in the Namib has been confirmed to perform it with the same reliable fog-triggered consistency. Namib unguicularis is, as far as researchers can determine, the champion of the headstand. The physics of what happens next is elegant. The beetle's shell, its elytra, is tilted forward toward the incoming fog-laden wind. Microscopic fog droplets, moving on the breeze at 15 to 20 microns in diameter, contact the shell and begin to coalesce. Each tiny droplet attaches to the surface, then encounters the next droplet and the next, until they merge into something large enough to feel the pull of gravity. At that point, the droplet runs, guided by the angle of the beetle's tilted body, forward, down the slope of the shell, along the beetle's thorax, and directly toward the mouthparts below. The beetle does not need to move. It does not need to find water. It stands in the wind at the highest point of the dune, and the fog delivers its drink directly to it, condensed from what was, moments before, invisible vapor in the air. In a place that receives almost no rain, this is not just a clever trick. It is the difference between life and death. In 2001, a paper published in Nature by Andrew Parker and Chris Lawrence took this phenomenon and made it world famous, with a twist that has since become one of the most celebrated and one of the most complicated stories in biomimicry. Parker and Lawrence examined the shell of a Namib darkling beetle under a scanning electron microscope and found something extraordinary: a surface covered in tiny, microscopic bumps arranged in a rectangular pattern. The tops of the bumps, they reported, were hydrophilic. They attracted water, lacking the waxy coating found elsewhere on the shell. The slopes and troughs between the bumps were hydrophobic, coated in wax that repelled moisture. The bumpy architecture Parker and Lawrence proposed was a fog collection system of staggering elegance. Fog droplets would stick preferentially to the hydrophilic peaks, accumulate, grow heavy, and then, because the surrounding valleys were wax-coated and slippery, roll off toward the beetle's mouth rather than spreading and being reabsorbed. The paper they published inspired engineers around the world, and it became the single most cited example of biomimicry in popular science literature for the next 2 decades. There is, however, a complication. Subsequent research found that the beetle Parker and Lawrence had photographed may have been misidentified. Later analysis suggests the beetle in question was probably not Stenocara gracipilis, as the paper stated, but a different species, Physosterna cribripes. And, more problematically, neither species had been reliably observed performing fog-basking behavior in the wild. In a 2010 paper published in Frontiers in Zoology, researchers testing 4 Namib beetle species in a fog chamber found that bumpy-shelled beetles did not spontaneously fog-bask the way Onomacris does. And when they measured the water collection efficiency of the bumpy versus smooth surfaces, the differences were minor. The surface architecture of the elytra may not be the primary mechanism by which these beetles collect water, at least not in the way that Parker and Lawrence originally described. What does this mean? It means that the story is more complicated than the headlines suggested, and in science, that is almost always more interesting. What is not in dispute, some Namib darkling beetles do collect water from fog using their bodies. The behavior has been observed in nature for nearly 50 years. The hydrophilic-hydrophobic surface principle, trapping moisture on water-attracting patches and channeling it over water-repelling ones, is real, confirmed in the laboratory, and has been successfully reproduced artificially. The beetles of the Namib, in their many species and their varied strategies, are genuine masters of fog harvesting. The specific mechanism, the specific species, and exactly which surface features do the most work, these are still the subject of active, unresolved scientific debate. And that debate has not slowed down what the beetle's biology has set in motion. The 2001 Nature paper, however contested in its specifics, launched a new field of engineering research, and the discoveries it enabled are reshaping how we think about water in the driest parts of the world. The core insight is this: fog contains water, vast quantities of it, in environments where rain is rare or absent. The problem has never been the absence of water in coastal arid zones. It has been the absence of a surface capable of catching what is already there. In most environments, fog droplets are too light to fall as rain, too diffuse to pool, and too small to be intercepted by any natural surface other than one specifically designed for the purpose. The beetles of the Namib found that surface, or rather, they evolved it across millions of years of selective pressure in an environment where every drop of water was a matter of survival. The architecture, whatever its precise details, works. engineers at the Massachusetts Institute of Technology reproduced the hydrophilic hydrophobic pattern surface in the laboratory, demonstrating that it could collect water from fog at rates significantly above those of unpatterned materials. Research groups from Chile to Morocco to Eritrea have built fog nets, mesh frameworks stretched across hilltops in coastal fog zones, based partly on the principles the Beetle's biology revealed. In some pilot deployments, fog nets have produced hundreds of liters of clean water per day in communities where rainfall is insufficient to sustain agriculture. The Warka Water Project, the FogQuest Initiative, the MIT Fog Harvesting Research Program, all of them in some form trace their intellectual lineage to the observation of a small black beetle standing at the crest of a Namib dune in the early morning dark. A company called NBD Nano has explored commercial applications, self-filling water bottles that condense moisture from humid air, the design of fog-free windows and mirrors, water condensers for arid construction sites. The list continues to grow as the engineering principle finds new applications. All of it from a beetle that has been solving this problem on its own back for tens of millions of years. To understand why the fog beetle solution is so important, you have to understand what the Namib actually is, what it means to be alive in a landscape that has been dry for longer than the Rocky Mountains have existed. The Namib is not simply a wasteland. It is a mosaic of hyper-specialized communities, each calibrated to the specific conditions of its microhabitat. The coastal strip, where the fog is densest and most reliable, supports a different set of species than the interior dunes does, where the fog penetrates only occasionally and the temperature swings are extreme. The interdune corridors, where moisture accumulates slightly in the compressed sand, support a different community again. What unites almost all of them is the Benguela Current, the cold upwelling that creates the fog in the first place. The current brings nutrients from deep water to the surface off the Namibian coast, feeding one of the most productive marine systems in the world. The fog that current generates pushes inland and creates one of the most biologically productive desert ecosystems in the world. The same oceanographic process feeds the seabirds and the seals offshore, and the beetles and the welwitschia plants onshore. It is a single thread connecting the deep ocean to the top of a 1,300-foot sand dune. The welwitschia itself deserves a mention because it makes the point about Namib time as vividly as any single organism can. Welwitschia mirabilis is a plant that grows in the fog zone of the Namib, producing exactly 2 leaves over its entire lifetime. 2 leaves that grow continuously from a central trunk for centuries, sometimes millennia, fraying and splitting as they age into a tattered tangle of ribbons. Individual welwitschia plants have been confirmed by radiocarbon dating to be over 1,500 years old. Some may be approaching 2,000. They are older than most human civilizations that still stand. They survive almost entirely on fog water absorbed through their leaves stomata. They are a living demonstration of what is possible in a landscape where fog is the primary water source and patience is the primary survival strategy. The darkling beetles live in that same fog-fed system on a much shorter timescale, but with the same fundamental adaptation. Intercept what the current delivers. Use the body as a harvesting surface. Do not wait for rain that may never come. One of the most remarkable things about the fog-basking beetles of the Namib is the precision with which their lives are calibrated to a specific environmental window, a zone that is too small for comfort, but large enough for survival. The fog arrives in the pre-dawn hours when the temperatures are their lowest. It is this cold that causes the condensation in the first place, the damp air from the ocean hitting the warm thermal blanket that builds over the desert at night, dropping its moisture as it cools. By mid-morning, as the sun rises and the air temperature climbs, the fog burns off. The dunes, bare sand under direct desert sun, can reach surface temperatures that would kill most insects within minutes. This means the beetles' fog harvesting window is narrow. They must be at the dune crest before the fog arrives, which means navigating in darkness. They must complete their drinking before the sun makes the exposed crest untenable, which means performing a behavior that leaves them utterly exposed in the middle of the dune's highest and most visible point, at the moment when predators are also most active. It is a trade-off that has been calibrated over millions of years. The beetles are black, which maximizes their ability to absorb heat when they need to warm up in the cool pre-dawn air, and which makes them visible against the pale sand. They retreat beneath the surface during the heat of the day, where temperatures in the sand at even a few centimeters of depth are dramatically lower than on the surface. They are nocturnal in their social lives, diurnal in their fog behavior, and underground for the worst of the heat. The daily schedule of a Namib darkling beetle is a masterpiece of thermal scheduling. And the fog itself, it turns out, is not a simple resource. The Namib experiences roughly 180 fog days per year on the coastal strip, but the distribution of those days is seasonal, unpredictable, and varies significantly across the geography of the desert. During dry years, when the Benguela's current upwelling patterns shift, fog frequency drops and the desert's moisture budget tightens. During those years, the beetles that can most efficiently extract water from whatever fog arrives, the ones whose surface architecture, behavior, and body shape are most tightly tuned to the harvesting problem, are the ones that survive to reproduce. That is how evolutionary pressure works. That is how, over 55 million years of exactly this landscape and exactly this fog, you end up with a beetle that has its water delivery system built into the architecture of its shell. The Namib desert beetle reminds us that hostile is a human word, not a biological one. What we see as a wasteland of sand and salt, these beetles have inhabited for tens of millions of years, longer than most of the animal families we consider ancient. They don't fight the desert. They read it. They harvest what it offers, in the narrow window when it offers it, with a body engineered over deep geological time to do exactly that job. The beetle's biology has already taught human engineers how to pull drinking water from fog in places where rain falls rarely or not at all. It will almost certainly teach us more as we continue to study it, particularly as climate shifts make water scarcity an increasingly global problem rather than a regional one. The most efficient solution to the hardest problems are often not invented. They are found in the topography of a shell, in the behavior of a creature standing at the top of a dune in the dark, tilting its body at exactly the right angle to catch what the ocean sends. We share this planet with millions of stories, most of them unfolding in the silence of the deep or the shadows of the canopy. Thank you for journeying with me into the world of the Namib desert beetle. I'm Patrick Viersba. There are many secrets of Earth, if you only know where to listen. I'll see you on the next horizon. Until then, follow our coordinates by subscribing to or following the show. It ensures you never miss a step into the unknown.